Okay, we'll get started. Okay, so reminder that next week is reading week. I'm sure you're aware, but there'll be no class next week. Assignment 2 is out. It's not due for a while, but like I said last week, I encourage you to start on it early because other stuff is going to pile up in other courses. And yeah, is there any questions before going into the lecture, maybe about assignment 2 or about anything?
Yeah, I have one.
Mm-hmm.
The use of the term backdoor. So I heard in an article that Apple sort of wanted data access for UK customers, and they coined the term backdoor to their users. Now, what I'm thinking is backdoor is supposed to be a secret, and if you go ahead and ask about getting a permission for a backdoor, isn't it like an unlocked front door?
So it's a good question. So I don't know how it's used, but I've heard it used in both contexts. So a backdoor could be something that people know about, but you can't go through it because you need a key. So like if Apple slips a key to the government and says, okay, now there's a backdoor, you can go through it. But usually that happens after it's revealed. Like usually it's secret, and then eventually like there's some whistleblower or something like that reveals that there was a backdoor all along, and that's how that term is used. So it's probably more likely the second, where it's a hidden thing. But when we learn about it, we use the term backdoor to describe it.
Once we learn about it.
We don't say, oh, it's not a backdoor anymore because we know about
Yeah,
it.
but they sort of made it public.
Yeah.
And how they are going to decide whether to do this or not. But they sort of, so it's public news. I mean.
Yeah. So the other term that's used sometimes is key escrow. So, or escrow, just escrow in general. So it's the same idea. It's that the government has a key that can decrypt things. And so that is usually a transparent system. Everyone knows about it, like it's just an escrow system. But yeah, it's an interesting point. Okay, any other questions, comments?
I have a question
Yeah.
about the assignment.
Yeah.
So in question 1, you said we should come up with a core taxes, but then is it based on our brainstorming of like how this should be done, or like is it also based on what we view the system beforehand?
So you should learn a bit about the system first, because you want to figure out what users would want to do with the system. Otherwise, you can't come up with the core tasks. So you might even use the system, play around with it, at least read about its features and like sort of what it's doing. And then after that, you would then try and brainstorm your core tasks themselves. Does that answer your question, or is it?
Yeah, because like I find it hard to like brainstorm like 7 core tasks without thinking about the system, or without like trying to know what the system is.
Yeah, so you can know what the system is and how it works to know at least what its features are to help you come up with core tasks.
Yeah, because like okay.
But the other thing I would say is that if you're like, oh, I can come up with 4 or 5 easy, but then 6 and 7 is like kind of hard. That's the struggle every student has every year.
Yeah.
So that's normal. That's sort of part of the challenge is coming up with 7. But
I thought we had to come up with the core tasks without like, because I feel like if I go into the system and I try to play around with it,
yeah,
I find okay, this can be the core task, and I
Right.
feel like it's a reverse psychology. Like, should I do this first, or should
Yeah.
I explore a system first?
So I understand your concern, but like, no, you can explore it first, and then it's sort of like what would user? It's kind of like a car. Like, what's a core task with a car? Well, before you've ever driven a car, you probably can't come up with tasks that you might want to do with a car, right? But once you've driven it, you're like, okay, well, how do I put on the parking brake? How do I put it in gear? How do I put on the 4-way flashers? There's all these tasks and things that you wouldn't know unless if you've driven. So you can sort of use the same analogy here. So, so you can assume you should know all the details of the system and then come up with a core task based on that. Yeah, that makes sense. Okay, any other questions? Okay, good. Okay, we'll jump into the lecture then. So you'll remember last week, not last year. Last week we started an attack tree for breaking HTTPS. And attack trees are based on just one goal of the adversary. It's not like breaking the entire protocol. It's narrowed to one attack. So the specific attack we were looking at was, let's assume I'm already in a man-in-the-middle position and HTTPS is between the sender and the receiver. Can I learn anything about the traffic that's going across that wire, or can I learn nothing? Okay? And so my goal is to learn something about the traffic. And so we decided to break it into three approaches, I decided. So one is, even if you can't see what's happening inside the tunnel, because there's a tunnel there, you could sit on the outside and still learn a lot of information, right? So you know at least the domain that's being visited, and then if you can look at sizes of packets and timing and things like that, and you can maybe infer even what websites are being visited. Today we're going to focus on breaking into the tunnel, and then we'll also focus on how to get the tunnel pointed to you. If you can get the tunnel pointed to you, then you can just read everything straight out of the tunnel. Okay? Now, breaking into the tunnel we'll tackle first. The way you break into the tunnel is you break the cryptography. And it's hard to explain how you break the cryptography without explaining to you how cryptography works. So for this part of the attack tree, I'm going to go very shallow. I'm just going to give you the intuition of a couple attacks, but I'm not going to go through the details of these attacks because it would take too long to explain all the crypto that's behind it. And crypto isn't a prerequisite for this course. So we'll take a light look at break into the tunnel, and then we'll move on to trying to get the tunnel pointed to us. Okay, so if you want to break into the tunnel, like I say, you want to break or somehow subvert the cryptography that's being used. And cryptography is very complicated. There's all sorts of different algorithms, and they have different purposes and things like that. But the main thing to understand about cryptography is that there's keys. And the way it works in the secure tunnel, at least at the very end of the protocol, is we have a system we call symmetric key. But basically, the sender and the client, like the server and the client, or the sender and the receiver, they both have a key. They both know it, so they know each other's keys, and nobody else knows the key. Okay? And if you, as the adversary in the middle, were also able to get a copy of the key, so now there's 3 copies, then you could read everything, you could modify everything, you could do everything that the sender and the receiver can do. Okay? So the whole goal of the cryptography, there's this handshake protocol that's done. It's done assuming an adversary's in the middle, can listen and change traffic. And it guarantees that even if there's an adversary in the middle tampering with things, you can arrive at knowing 2 different keys, or 2 parties knowing the same key and the adversary doesn't know the key. Okay? How you do that is sort of the magic of cryptography that we won't cover. Okay? But anyways, from an attack tree perspective, if we can get the key, we can break the tunnel. Okay? So we can just focus in on getting the key, and then there's a couple other things we can do as well. All right, so the sender, the client, and the server, they both have a key. I want it. I'm the adversary. How do I get it? Right? So I could try and steal it from either side, either the client or the server. So I have 2 targets that I could steal it from. Or the other approach I could do is I could try to somehow break into the tunnel even though I don't know the key. Okay, and this is going to use more advanced cryptography. So we can get our heads around the first one, and then the second one's a little hard to understand without all the crypto details. Okay, so how can we steal a key? So one approach that we can use is something called side channel analysis. And so side channel analysis is actually a big concept that is applicable in all sorts of security situations. So it's not just applicable in this case, it's used. And I'll give you a bunch of examples of where it's used. But the basic idea is, let's say I'm attacking the client, okay? The client has the key and they're actually using it like every time someone connects to them, they use the key. Someone sends them data, they decrypt it, they use the key, okay? And after they use the key, they usually do something in response. So they might send back a message. They might say, oh, there was an error with that ciphertext. I couldn't decrypt it. They might be able to respond fast. They might respond slow. We don't know, okay? And so the idea is what we're going to do is we're going to, from our position in the middle, is we're going to look at how long does it take the client to do these decryption operations based on what we can see. So we'll send it some messages to decrypt, and if it decrypts them fast, we say, okay, that's fast. If it decrypts it slow, we say it's slow. And the idea is that depending on what the value of the key is, we could actually learn some information about the key based on how fast or slow it can decrypt different kinds of messages, okay? Now, there's a bunch of math that goes into the type of algorithms that are used. These attacks don't work anymore because once people realized that what they did is they changed the cryptographic code so that it wouldn't take shortcuts. The main problem, the reason these attacks worked is the encryption was based on math. So, for example, if you had a key with a whole bunch of zeros in it, that's kind of like a small number. And when you do the math with a small number, it doesn't take very long. And if you have a key with a whole bunch of ones, that's a big number. And if you're doing the same math with a big number, it's taking longer. Okay? That's sort of the intuition behind it. All right? So what they did, the people who write cryptographic libraries, is they changed the implementation so they're always slow no matter what. So if your key has a whole bunch of ones, or if it has a whole bunch of zeros, it's going to be just as slow in either case. Okay? So they make sure that every implementation has constant time. All right? And if you do this, then you can eliminate these timing attacks. But for a while, these timing attacks worked, and they were actually pretty reasonable. You could actually sort of do it over a network. It wasn't just a hypothetical attack that would work in like a laboratory setting. You could kind of do it on the wild in the internet. But you had to send lots and lots of packets and have it decrypted to take lots and lots of measurements. And what would probably end up happening is if you did this attack in the wild is it wouldn't break down because of the cryptography. It would break down because the firewall or some intrusion detection system or something like that would say, you're sending too many packets. We're going to cut you off. Okay? But anyways, so the idea is that you have encryption. You have to implement it. And the security that encryption gives you, like people don't really consider the implementation of it. Like they work at the math level. Like the equations work. Therefore, the equations give you all these security properties. But sometimes we forget that you have to translate this math into code. And when you translate it into code, there's other ways that you could attack the more the code or the implementation of the system. So timing would be like one of those kind of side channel analysis. So there's lots of other things that aren't related to HTTPS where this kind of looking at these side channels shows up. So here's some examples of them. So early ATM, so these are like bank machines where you get money out. You put your PIN into an ATM, and every time you press a key when you type your PIN in, I'm not like an electrical engineer, but it like does there's some like voltage or resistance or something like that. Like something about the power consumption of it changes because you're pressing the button, and then when you let go of the button, it changes again, okay? And the way the ATMs worked is that different keys would have they would create slightly different patterns in the power consumption. So if you press the 1, it would look one way. If you press the 9, it would look slightly different. And if you had a very sensitive sensor that was measuring the power consumption, you could actually read the PIN out by looking at the patterns that it produced. There were some voting machines that were similar, but in this case, it was the same idea. Different buttons produce different patterns, but here they were looking at electromagnetic interference. And so someone was actually standing outside of where people were voting. They had a radio that was very sensitive, but it was still a consumer radio. And every time someone would press a button, you could hear like kind of, I don't know, like a fuzzy noise or something like that, like a certain tone. But like the tone would be slightly different if they were pressing the first button, second button, or third button. And so you could actually read off how they were voting based on the frequency that the interference was coming out of. So you'll see that I mentioned the encryption algorithm called RSA. So RSA stands for 3 people that invented that algorithm. The middle person, the S, his name's Adi Shamir. And so I remember when I was a grad student, like you, he came to my university and he gave a talk. And his talk was, I had like an old desktop computer, like not our modern laptops. You have to go back, back when I was a grad student, so like a couple decades. And I noticed that these computers, they're really loud. They're making these weird like clicking and hissing noises, and like I don't really know what is that? Why is that sound coming out? I don't really understand it. But he had this idea of like, let's say I was doing decryption and it started like making these weird clicking noises. Like, is that somehow correlated to the key? Like if I decrypt with one key, is that like clicking going to sound a little different than if I use a different key? And so without like trying to reverse engineer where all the sound comes, he just did some experiments where he decrypted with a bunch of keys. He like recorded it with a microphone, and then he tried to correlate the key to those sound waves, and he found that you could do it. So you could basically, if you had a sensitive microphone, you could train like what the sound waves look like for different keys, and then you could just read the key off based on the sound that the computer was making when it was doing decryption. Other things are, so your phone usually has actually a very sensitive gyroscope. So a gyroscope is so that the phone knows what orientation it is. So if I'm going to take your picture like this or this, it will flip on the screen because it knows the difference between the two. But it's so sensitive that as you type, you're kind of vibrating the phone, you're tapping against the phone, it can measure the taps. And if I tap a letter on a virtual keyboard that's way out on the outside of my phone, I'm going to like rotate the phone a little bit more. And if I tap it near the middle of the phone, like where I'm holding it from the back, I might tap it a little bit less. So basically, whatever key I'm pressing, it's going to look slightly different in terms of the vibration it makes on the phone. And so again, if you train, you have to train first, but if you train, you could read someone's password from the gyroscope data. You could figure out what keys they're pressing, and then you could figure out what password they're typing in, just based on having access to the gyroscope. There's also work on, there was this whole attack called Tempest, where they would look at reflections. So like right now you can see what I'm projecting on the screen, but you can't probably see my laptop screen. But I am wearing glasses, and you could probably see the reflection of the screen in my glasses. So let's say you took a picture of me. Could you actually reconstruct what's on my screen based on the reflection in my glasses? And the answer is yes. Like you can do that like fairly easily, and you don't need super high resolution or like really fancy cameras to make that work. And so, and then you can, sound reflects off glass as well. You've probably seen on movies where like people have these devices where they shoot like a laser at like a glass that's like in a building across the street or whatever. And then they have headphones and they can like hear the conversation because the conversation's making the glass resonate, and then the laser is like measuring that resonation, or it's translating it into like a light signal. So anyway, all this stuff we call it side channel because normally when you design a system, you don't take it into account. It's not in the main channel of what you're taking into account. It's based on how it's implemented, and then attackers don't care, right? If I can attack a system with a side channel, it doesn't matter. As long as I can attack the system, I don't care if I use a main channel or a side channel. So attackers are going to use every possible way of attacking a system. Okay, here's another attack. So this attack is a vulnerability. So again, this has to do with how things were implemented. This attack is called Heartbleed. It was pretty famous when it happened. So like if you picked up CBC News or the Globe and Mail or the New York Times or something, you would read about this attack. It might not be on the front page, but it would be in the newspaper. Okay, so that was like kind of the level of that it was at. Okay, so Heartbleed, before we get to Heartbleed, let me just explain a bit about how HTTPS is implemented. So you have a client and you have a server, and both of them have to have libraries that support HTTPS. So for the user, the library is going to be sitting either in the operating system or in the browser, maybe both. And then depends which one you use. If you're on a Mac and you're using Safari, your browser and your operating system are the same. So you're going to use what's called S-tunnel. But if you're using Chrome on Windows, are you using Google Stack or are you using Windows Stack? Like that, there might be a difference. So it might, or if you're using Firefox, you might use either the browser or the operating system. Similarly, the servers serving up websites. Okay. And so servers run different operating systems, and a popular operating system is the free open source operating system called Apache. And there are free open source client operating systems like Ubuntu or Linux and different flavors of Linux and things like that. They're not super popular because why are they not super popular? Well, you kind of have to be a computer expert to use them. That's maybe Ubuntu people think that that's not true, but most people think that like Windows or Apple is going to be a lot more user friendly. Okay, and so most people are going to prefer to use Windows or Apple as opposed to Linux. Okay, but servers aren't usually run by normal people, right? Servers are run by people who have an expertise on setting up a server, which means that you probably have some technical ability, and so using an open source software, Linux-based software, isn't going to scare you off. Okay, so the usage of Apache is like way more in the server world than say Ubuntu is in the client world. Okay, so lots and lots of websites use Apache. If you install Apache at the time, so this attack is a little old, you could turn SSL on. Basically, it was just a configuration option. You just say, yeah, I'd like SSL. And so they'll say, fine, you know what, we shipped with the operating system an SSL library called OpenSSL. It's there, it's ready to go. You don't have to use it if you don't want to, but it's the default, okay? And back in the usability lecture, you saw that most people don't change their defaults, okay? So most people that install Apache, there's no real reason not to use OpenSSL. It's there, it's one click away, and now all of a sudden you support SSL. Okay, so something like 40 to 60% of websites were running on this kind of architecture. All right, now OpenSSL is, it's pretty old software, and it had a bunch of features in it. Actually, the person who wrote it originally, I think he said, I wanted to learn C++, I didn't know C++, so I thought I'll implement SSL, and then I'll teach myself C++. So that's where OpenSSL came from. But anyways, it had all these like weird, like undocumented or underdocumented or at least underused features that were just part of it that people kind of forgot about. They forgot that it was there and no one really used it. And so one of the features was this thing called Heartbeat. Okay, so it was part of OpenSSL. And the idea of Heartbeat was, it was basically a way of kind of like pinging a server to figure out whether they support OpenSSL or not. So I walk up to a server, I just want to know, do you support OpenSSL? Yes or no? So I could use this Heartbeat protocol. And basically what I would do is I would shoot some bytes at it, and then I would say, repeat it back to me. So I'd say ABCD, and it would spit back ABCD. Okay? And if that worked over the right ports and that type of thing, then I'd be like, okay, OpenSSL is up and running and operating on this server. Okay. Now another feature of Heartbeat, I'm oversimplifying everything, but just giving you the intuition, is you could effectively say, I'm going to shoot you a bunch of bytes and I want you to repeat it back to me, but don't bother like repeating the whole string back to me. You can just, give me the first 5 characters and that's okay. Okay, so you could send a second parameter, and the second parameter would just say how many bytes you want it back. Okay, so you might want 5 back, you might want 1 back, you might want 2 back, right? You might want -10 back. What would happen if you asked for -10 back? What if your string that you sent it was 7 bytes, and you said, give me 20 bytes back? Okay. So, okay. So anyway, these are, from a security mindset, these are the questions you should ask, okay? So you're giving a buffer, right? And because you're giving a number to go along with it, you could overflow or underflow the buffer. depending. And so the code should check it, right? It should say any integer less than 0 is not allowed, and any integer that's greater than the length of the string that I received is not allowed as well. So you should do bounds checking on it. This code was not doing bounds checking, okay? And remember, I just told you it was this guy's C++ pet project. That's also important because C++ itself doesn't do, like, there are different languages where when you write a string into memory, the length of the string is encoded along with the string itself, like Java, for example, okay? C++ doesn't have any of that. In C++, you just say the string starts here. This is where I stored it. And then that's it. And then you just read the string until you hit a null byte or something like that. And then you say, okay, I'm done. Okay, so what happens if you say, hi, I want to know whether you support OpenSSL. If you do, please repeat back the first 1,000 characters of the string A, B, C, D, E, F, G. Okay, so this, again, should throw an error or something like that, but it didn't. Okay, so OpenSSL was not hardened against this particular attack. So what it did instead is it went to the memory location where the string A, B, C, D, E, F, G was stored, and it read the next 1,000 bytes and then sent all of that 1,000 bytes. Okay, so basically where the string is and whatever else is in memory beside the string gets returned back to the user. Okay, and you could ask for a lot of data. You could ask for about 64 kilobytes of data, which is quite a bit. Okay. Now, the other thing about it is that memory works in a stack, so it's first in, last out. So the stuff that's beside it is the stuff that was sent before it, kind of thing. Okay, the stuff that it put into memory before it put this string into memory. That's the kind of stuff that's sitting there. So for a web server, a website that's running a web server, what kind of stuff would be sitting in memory on a web server? That might be sensitive, for example. Okay, so if you log into a website, you send your password. It has to put that into memory because then it has to hash it and match it to it has to pull the hash out of the database and match it. So that's sitting in memory. Yeah? So passwords, what else? Yeah, so any kind of request would be sitting there. But what could be inside a request that would be sensitive? Okay, so private keys could be there. What would they be private keys of? So it could be user sessions. So past users that connected recently over HTTPS, it would have to keep those keys in memory because it's going to have to use them to decrypt the traffic as it comes in. Yeah? Okay, so session cookies, another thing. So we haven't talked about them yet, but basically after you log into a website with a password, the website kind of sets up kind of like a secret in this thing called a cookie, and that's how it keeps you logged in to the website. So all those session cookies are sitting there. Okay, so it could be logging of events. Yep. So authentication and session tokens, cookies, they're all kind of the same thing, but yeah. Certificates are public. So we haven't talked about certificates yet, but they're not secret. But there is something connected to that could be there. We'll talk about. Sorry? Yeah, sure. Yeah, so an API key, something like that. Yeah. Yeah, so we are attacking the server, not the browser. So we're only going to get secrets that are on the server, not on the browser. But almost all the things we talked about, there would be a copy as well. So a session token, both parties have to know it. An encryption decryption key, both parties have to know it. A password, it has to process it. So it needs to know the plain text password to process it. So even though you might associate these things with like browser secrets, they are things that would enter the RAM or the memory of the server at some point and could be sitting there.
So what I'm saying now, why would I go to, I mean, attacking an Apache server when I literally like I get it from the browser?
Oh, I see what you're saying. Okay, so this vulnerability existed on server. So it was an Apache browser. Most user browsers don't use OpenSSL.
Yeah, but you know the traffic goes through SSL. Now, another question is, what's the default port? Is it 8080 or 443? Because now you know that
Yeah.
HTTPS is 443. Now, if you say an OpenSSL and literally going between 8080 and 443, so what's it? Because, I mean, it's OpenSSL and it's still going to the default port, which is even the secure port. So, I mean, it doesn't really make any sense.
Okay. This attack is exploiting this protocol, this heartbeat protocol, yeah? The heartbeat protocol, so it's bad code. There's nothing wrong with the protocol. It's not a protocol issue. It's bad code, yeah? And this code is only in OpenSSL, and OpenSSL more or less only runs on Apache. Yeah, and even if OpenSSL was being used on Ubuntu or something like that, because you're not a server, you're not going to have this heartbeat thing turned on. Yeah, so basically no browsers were vulnerable to this. The bad code was just on servers that had this exact stack of technology, and that's it. Yeah, if you could choose who to attack, let's say every computer had this vulnerability, of course you would go after the browsers instead of the servers. Or maybe, I don't know, you probably go after both, but yeah. But we couldn't choose in this case. It was just, yeah. So the most recent 64 KB that's on the server's working memory will be compromised. Yeah, exactly. So if the server if you can get the key, it doesn't matter how strong the encryption is, yeah? And so if the key's sitting there, it's over, yeah. Okay, so usernames, passwords, cookies, data just in general, like things that people submitted to the website. They filled out a form. They put their address in, their credit card number, all that kind of stuff you could pull off. Now, there was one sort of thing that people weren't sure whether you could use Heartbleed to do or not. So I didn't go through the details of the cryptography, but there is a key that's really, really important that belongs to the server. And it uses it to set up every single SSL connection it has. So you do this sort of handshake protocol using what's called the long-term secret. And when you're done the handshake, then the user and the server, they both end up with a copy of a key, but that's unique to them. So if a server has 1,000 users, it has 1,000 keys with each user, okay? But in order to get those 1,000 keys, it does have one key that it used for all of them, okay? So this is like the most important key. Now, it is sitting in memory, okay? So you could, in theory, use Heartbleed to get it out, to get it out. But there's only one issue, which is more of a practical issue, which is that because this key is like the basis of all your SSL connections, it's more or less the very first thing you load into memory. So you load this key into memory, and then you do a bunch of stuff. You're collecting data, you're stuffing memory with other stuff, then you free it up, and then you stuff it and you free it up. But this key is always so deep in memory because it was loaded first, that if you can only pop the most recent 64 KB, you're never going to get deep enough to get to that key. Yeah? And yeah.
Is the maximum 64 KB you can get from the server?
Yeah, so the maximum is just in this heartbeat protocol. So like that was the maximum that the code would allow. It would crash if you did more than that. Yeah. Okay, so the question is, could you ever get that key? If you could get that key out, it's not like it's one thing to attack the server here and now. I get whatever data happens to be in the server. But if I can get that key out, then I can compromise that server for as long as it continues to use that key. Okay? And then we have to go and we have to get rid of the key, revoke it, and that's going to be a whole process. And it's a big deal. Heartbleed is a big deal, period. But getting that key is even worse. So there were some companies, I forget which one it was. I think it was Cloudflare or someone like that. And they speculated that you probably couldn't do it on any of their servers because they've been running for so long and they have like uptime of years maybe. And there's so much data there that like you could do a lot of damage with Heartbleed, but you would never get that key. And so hackers took it as a challenge to try and get that key. And so what they did is they figured out a way of forcing a reboot. So they used one exploit that would force the server to reboot. And then because it rebooted, it loaded that key into memory. Then they hit it with Heartbleed right away, right after a reboot. And then they were able to extract the long-term signing key. So they were able to prove that you could even get that key out of it. So basically this was like a complete failure for any server that ran this architecture. You had to assume that all your user data was gone, your passwords were compromised, even your long-term SSL key was compromised. So that's why this attack like kind of made it to the news. And there was even someone who like was just a kid. I think he was in high school, and he was like playing around with this, and he thought, oh, I wonder if like the government of Canada, let's go to the tax service, CRA, and see if they're vulnerable to Heartbleed. So he tried it, and it worked. And he downloaded all sorts of like SIN numbers and things like that. But the problem was they were keeping logs. And so it took them a couple months, but a couple months later, the police show up at his door and charge him with hacking. So this is a warning to you, right? You might be curious about things, especially as security people. You have to be careful about deploying your knowledge, right? Even if it's just for fun. Now, eventually the case was thrown out. They agreed that, maybe he pled guilty, but then he wasn't really punished. It was just sort of a slap on the wrist, like sort of don't do this again, kind of thing. But anyways, it was real ramifications for him. Yeah, so if you were not running these three things, it would not work.
No, I mean I'm running an Apache server.
Yeah.
But my SSL is in third party.
Yeah.
Got the SSL from third party. Is it going to counter the app?
Yeah. So any of these three things. So you could not run Apache. You could run Apache but run any other SSL thing. Or you could even run Apache and OpenSSL but just have Heartbeat turned off. Yeah, and in any of those cases, that you wouldn't be vulnerable to it. But the 40 to 60% here was like, that's how many web servers had this exact configuration. So it was a popular configuration. Yeah. 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 Okay, great question. So if OpenSSL is not in C++, it's in Rust or Java or something with like safety and type strong types and all that type of stuff, yeah, then this attack goes away.
So you're saying it's generic to the programming language?
Yeah, so the programming language doesn't help, let's say. Yeah, so there's no automatic bounds checking or anything like that on C++.
How did they fix it?
So they just removed Heartbeat, basically. They said no one uses it anyway, but then everyone had to update, and it was an emergency, and you had to update tomorrow. You had to update yesterday, kind of thing. And yeah, so then, but they took this code right out of it. Yeah. And then people were really scared about like what else is in OpenSSL, right? It was also like kind of like, if this code is there, what else is there? So I think they went through with a fine-tooth comb, and I think they found other stuff, but nothing was exploited in the wild. And it was also researchers who found, actually, I don't remember. I think it was researchers who discovered this attack. And so I think they disclosed it to OpenSSL first. But I guess maybe because servers didn't update, there was lots of servers that were left vulnerable. I forget what the story is about the disclosure of it. But yeah, I'm pretty sure it was academic researchers that found it. So it wasn't like just discovered in the wild like a 0 day. I don't know why that's there. Okay, here's some other ideas about how we could subvert the crypto. Okay, so another thing that happens in SSL, I think I mentioned this last class, but you have different version numbers. You have SSL 2.0, 3.0, you have TLS 1.0 to 1.3. And then even within a version, like say you're doing TLS 1.1, you also have a bunch of different crypto algorithms that you could use. So you could be like, I want to use what's called Diffie-Hellman, or I want to use RSA, or I want to use AES-CBC or AES-JCM or whatever. So there's a bunch of different, you have different parameters, and there's different key lengths and things like that, okay? So the which version you end up using and which crypto algorithms you end up using is a negotiation between the server and the client. The server basically has a preferred list. So they have a list of like, this is the order in which I prefer algorithms. And you can go to the server and say, give me your list. And then you look through the list and you say, you basically start at the top and you go down until you hit one that you support as a client. Then you tell the server, I support that one. And then that's the one that you should end up using, okay? Now the problem is that at this point, this negotiation, you don't have the cryptography in place yet. You're negotiating what cryptography to use. So the cryptography is not there yet, okay? So that means that this negotiation is happening over a channel where the adversary is in the middle and the adversary can do stuff to it, okay? You don't have your tunnel yet. You're setting the tunnel up so you don't have a tunnel. If you already had a tunnel, then you don't need to negotiate it because you already have a tunnel, okay? So handshakes are done in the clear. And then after the handshake, then you have a tunnel, but the tunnel is based on the details that you negotiated in the handshake. Okay, so this leads to a natural thing, which is if the adversary's in the middle and the client's like, I want to talk TLS 1.3 because that's the newest version, the adversary can just switch that to I want to talk SSL 2.0, which is the oldest thing, and then the server, for backwards compatibility reasons, it doesn't want to use SSL 2.0. But every now and then someone fires up their Windows 95 machine that hasn't been patched, and they still want to serve the website to that user, right? And so they're still going to support it. It's going to be in there somewhere. They don't want to do it, but they'll do it. And so anyways, so that's the basic attack. So we call that a downgrade attack, where the adversary's in the middle and they're going to either downgrade the version of SSL or they're going to downgrade the crypto that's being negotiated. Okay, so does this attack work? All right, and the answer is that it shouldn't. So SSL should be designed in such a way that this attack doesn't work. So the basic trick, I'm not going to test you on this, I'll just give it to you for your own interest because it involves some crypto details. But basically what you do is you do the handshake, you're sort of optimistic that there's not an adversary in the middle, okay? Then what happens is you end up with keys. And all the negotiation that you do, it concerns whether or not your secure channel will keep messages secret, okay? So you're negotiating things to do with the encryption side of things about keeping things secret. But what's non-negotiable in SSL, what you can't negotiate, or at least in older versions, is the part of the cryptography that gives you message integrity, which is whether messages were changed in the middle or not, okay? So even at the results, even if you're fully attacked and fully downgraded, at worst, you have no encryption, so all your messages are in clear text, but you still have message integrity. So you can still check whether messages are being modified or not, okay? So what you do is you do the handshake, and then when you're done the handshake, before you start using the channel, you do a quick check. You basically, the client will say, hey, we just did this handshake. Now that we have our keys in place, I'm going to tell you everything that you told me during the handshake. And I'm going to apply my key to that, and I'm going to send it. And now the adversary can't do anything about it. So if the adversary changed the messages, then what your recollection of the handshake was is going to differ from what the server saw. Yeah. And because the key is non-negotiable that protects the integrity of the message, the server will receive the right message. And then they'll have a chance. Or the adversary can drop it, but then the whole connection drops anyways. And if the adversary changes it, they don't have the key, so that it would be detected. Okay, so that's sort of how SSL gets around downgrades. Now, the way it's implemented sometimes is different than what the specification says, or sometimes the specification doesn't give all the details, and so it leaves some things open, and then you get bad implementations. So for a variety of reasons, there are downgrade attacks that worked, but it was more attacking the implementation rather than the protocol itself. So what you could do is there were a bunch of different things. The first thing is that if you could downgrade the version of SSL to 2.0 or 3.0, then you could do a lot of damage as an adversary. And so when TLS 1.0 came out, they basically banned downgrading, at least to SSL 2.0. So all libraries would just not allow you to use SSL 2.0 anymore. So the lowest you could go was SSL 3.0. There were another question you could ask is, okay, let's say an adversary is able to downgrade you. What's the worst encryption that they could use? If I could downgrade you to like the worst level of encryption, what is that worst level of encryption? And so it turns out that the worst level of encryption that is supported at some point in the history of SSL is keys that are 40 bits long. Okay? 40 bits is something that I could crack on this MacBook in seconds. Okay, like very, very insecure. I can brute force all 2 to the 40 possible keys. Okay, why is like encryption that weak inside of SSL? Okay, is it because when we first put SSL in like the mid 90s, is it like 40 bits was the best that we could do? The answer is no. Actually, at the time, usually we used what was called DES. It had 56 bits, or we used triple DES, which should have triple 56, but for complicated reasons, it only has double. Doesn't matter. But anyways, what happened at that time period, is that SSL was invented by Netscape. Netscape is a company that makes browsers. Netscape is a company that's based in the United States. It's incorporated in the United States. Therefore, it's under the laws of the United States. At the time, in the 90s, early 90s, the US government said that encryption is regulated. If you export, say, a library software that implements encryption, if you give it to a user in some other country, it's equivalent under our laws as if you mailed them a bomb or a hand grenade or a weapon or something like that, okay? It's like giving military secrets, okay? You can do it. You can give bombs to people, but not to every country, okay? But Netscape, they want to give Netscape to whoever in the world wanted to use it, okay? And so what the government said is, okay, they sort of reached a compromise and they said, we'll allow you to export encryption, but it has to be 40 bits or less, knowing full well that they could break 40 bits. And so that's how it got implemented. So Netscape originally had 2 versions of their browser. They had a browser for Americans, and it had strong encryption. And then they had a browser for the rest of the world, and the rest of the world was limited to 40 bits. But then when they were releasing the software, there was a screw up. I don't know, something happened, and the version for Americans didn't actually get released. And so they ended up releasing the 40 bits to everyone. So basically everyone had 40-bit encryption, whether you were American or not. Then the laws changed. So Bill Clinton was president and he passed some laws, and then they removed that restriction, and then they could do strong encryption again. The problem is some of people were still running the old versions of Netscape that still only supported 40 bits. They hadn't upgraded yet. So for backwards compatibility reasons, the 40 bits sort of stayed there. So you would prefer to do strong encryption, but you would support weak encryption if either the server or the client was old. Yeah. So anyways, recently, like not that recently, but like maybe 5 years ago, people discovered that there are downgrade attacks on certain clients where you can trigger 40-bit encryption again. And so that's one of the attacks on the implementation. Okay, here's another attack. This is like an example of a pretty sophisticated attack. So these ones are pretty simple. the ones that we saw before, like downgrading and well, Heartbleed is maybe a little complicated. But I want to, again, I'm not going to test you hard on the details of this, but I want to give you the flavor, the intuition of kind of like what a more advanced attack would look like. Okay, so this is the setup of this attack. So it's called crime. And what I'm going to imagine is there's a user and they're on a website. And for some reason, I'm the adversary. I'm in two positions. I'm in the middle. But in addition, I'm also able to insert some malicious JavaScript that's running in a frame that's on the website that the user's on. I could also trick them to come to my website, but it's a little easier to just get an iframe on some website. So how could I do this? Well, maybe I could take out ads or something like that. And if the user's on a website and it uses ad libraries and it farms the ads out, then maybe it would give an ad to me, and maybe the ads would support JavaScript, and then I can run whatever JavaScript I want. Okay, so I get some JavaScript that's running on the user's browser. Okay, and what I'm going to do in this attack is, instead of attacking all the traffic that's being sent over HTTPS, what I'm going to do is I'm going to try to just take out tiny bits of traffic. Take out a byte here or 2 bytes here, and maybe I could scale the attack up enough to extract, 20 bytes or something like that. And getting 20 bytes out would be enough to, say, get a cookie value or something like that. Okay, so I'm not decrypting all the traffic that's going over HTTPS. My goal is just to extract a couple bytes of information, which I shouldn't be allowed to do. Right? HTTPS should protect you from the adversary from extracting even a couple bytes of information, even if the adversary is in the middle and even if they're running JavaScript, right? Like, you should allow the adversary to do all of this stuff, and you should still expect that your secrets that you transmit over this channel will stay secret down to like the last bit or byte of it. Okay, so this setup of having an adversary on the wire, running a website, and then inspecting traffic as it goes over, it's the basis of actually a bunch of attacks. So there's a cluster of attacks on HTTPS. They use slightly different methods for extracting partial information. So there's an attack called Beast. It exploits the fact that the encryption is what we call deterministic. You'll learn about CBC mode block ciphers maybe in 6110, and you might circle back to this attack. Some types of encryptions will pad out. So like you have some data, but you need 256 bits because it's processed in blocks of 256 bits. So you're going to pad the end of it. But depending on what the message is that you're inserting, when you pad it out, you might pad out to the nearest block, or you might spill over into the next block. And so that's a tiny, tiny difference that you could try and measure to see if there's any differences there. And then there's a stream cipher that's supported called RC4, no longer supported, but it turned out that it didn't have good randomness. It wasn't good encryption it was weird, but it was an algorithm that basically spits out random numbers. You mix the random numbers with your message, and that's how it encrypts it. Yeah, and to generate the randomness, it had an algorithm that would kind of churn, and then it would start spitting out randomness. The problem with it is that they didn't churn it long enough, and so it started spitting out things that weren't perfectly random, and then eventually it became perfectly random. But there were some biases in the randomness at the very, very start. So anything that was encrypted at the very start was like susceptible to unpredictable or predictable randomness. Anyways, whatever. These are different like nitty-gritty crypto details, but it's basically the same setup. Now, the one that I'm going to talk about is easier to understand. So it's called crime, and the C in crime stands for compression. So compression is the vehicle that we're going to use. So compression is in the TLS standard, but it's not really used. So you can do compression, but people don't really use it. There was an alternative to TLS that people played with for a while called Speedy. So Twitter, Google, a couple of the big companies, they use Speedy for a while, but they don't use it anymore. But there was a time when Twitter was served over Speedy. And then HTTP also has support for compression. Okay, so it's kind of there, but it's not always turned on. But what we're going to assume for the purposes of this attack is that it is turned on. Okay, so we have some compression. So what is compression? Just at a high level. I'm not looking for a grand explanation. So I'm going to send you a message, but before I do it, I'm going to compress it. What does that mean? Okay, so I'm going to shorten it. I'm going to squeeze it. And why am I able to, like if I compress, am I throwing away information? So when you get the message and uncompress it, do you get exactly what I sent? Or is it like I threw away a bunch of stuff so you can't recover it anymore? Okay, so compression is meant to be lossless. There are actually different kinds of compression. So if I'm sending you music or video, it could be a lossy compression. So you do lose a bit. You don't get back exactly what I send. But if I'm sending you packets and they're signed and they have max and all this stuff, you don't want to lose even a single bit. Okay, so all the compression that we're talking about here is lossless compression. Okay, so what that means is I compress it, I squeeze it, I send it to you, you unsqueeze it, and when you unsqueeze it, it's bit for bit exactly what I put into the compression algorithm. Okay, is there any limit to how much I can compress? Can I always squeeze things down to a single byte and send you a single byte, and then you can blow it back up into every email that's possible? No. Okay. So there are going to be some limits to it. Okay. Do all messages compress equally well? Give me an example. Give me an example of a picture. Let's say I take a photograph. What's the kind of photograph that would compress well? Okay. So lots of repetition of the same color. Yeah, whether it's all zero like black or white, but it could be any color. So let's say I give you a picture and there's a sky and it's blue, right? Instead of sending you every pixel, what I do is I just say, there's this shade of blue and I want you to fill the next million pixels in with that shade of blue, right? And giving you that instruction is a lot shorter than saying blue, 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 blue a million times, okay? That's how compression works, okay? And so at a high level, if there's a lot of patterns in the data, it will compress well. If it's completely random and there's no patterns, it's not going to compress at all. Random data basically doesn't compress. Yeah? Okay? So any repetition, if you repeat the same thing a bunch of times, it's going to compress well. If there's no repetition, it's not going to compress. Does that make sense? Okay. Now, let's go back to this attack. So Mallory's sitting here, and she's first off running some JavaScript. Okay, what can she do by running JavaScript? Okay, one thing that she can do with JavaScript is she can ask Alice to go fetch any data from any web server in the world. Okay, so she can be like, go over to Google and download this image. Go download the Google icon from this URL. Okay, and she can do it a lot of times. I mean, JavaScript, it's running, so it can, every second it goes and fetches that image over and over and over again. Okay, now what Alice's browser is doing is it's creating an outbound connection, and it's sending a request to that server and say, give me the image, and then the server sending the image back. Okay, now let's say that Alice is logged into Google. Okay, another thing that happens is that Alice's browser will say, oh, you're about to go ask Google something. Let me check real quick and see if you're logged into Google. If you are, I'm going to take the cookie value that represents the fact that you're logged in, and I'm going to put that into the outbound connection. Okay? So the browser will drop the cookie value into what's called the header, and then the request gets put on the end. Okay? And all of that gets sent over to the server. And we're going to assume that this is going over HTTPS because most people won't let their cookies get sent over not HTTPS for reasons that we'll talk about later. But basically, if you can steal the cookie, you can log in as the user. Okay. So what the adversary can do is she can force Alice's browser to send a lot of connections with a secret cookie value. Okay, so she can open up a million different connections, and they all have the same cookie value that's put into the header of it. Okay. Now, that doesn't help her because it's encrypted. Yeah.
Where exactly is Mallory sitting on the left? What is that?
So this is Mallory. She's on the wire, meaning, is that what you mean?
No, on the left.
And then here it's just showing that she has JavaScript running in a website so this is meant to be a website. Yeah. Okay, so basically she's using JavaScript to initiate a whole bunch of connections to the same server and the same cookie values getting put into the same request. So she's seeing millions of copies of this, but it's encrypted. It's going by the wire. Okay. Now, last class we said, well, if things are encrypted, you can still see the length of it. Okay, you don't know what the data is itself, but the length of it is one thing that you can see. Maybe it's rounded up to the nearest byte if it's a stream cipher, or the nearest 128 bytes, or 256 if it's a block cipher, or whatever. You can see the rough length of it. Okay, all right. So this is the setup of the attack. Now imagine that compression is also turned on. Okay, so what Alice's browser is going to do is it's going to drop the cookie in. It's going to take the request. So the request is like the name of the image that you want to download. By the way, who gets to choose the value of the request here? So it's purple because Mallory's choosing it. So Mallory can choose to send you to Google or Facebook with JavaScript. She can say, go ask for logo.jpg, go ask for abc.jpg. Like she fully controls whatever is appearing on this side, okay? She doesn't see the cookie. The JavaScript doesn't see the cookie, okay? The browser's putting the cookie value in, okay? But it puts the cookie value, it puts the request that Mallory was able to choose, it compresses it, then it sends it over an encryption channel, and Mallory can see how long it is, okay? And how long it is actually telling her how well it compressed, okay? So in other words, she can try different values here. So the request here, she can pick whatever values she wants, and then she can, press a button and basically learn, did that compress well or did that not compress well? That's the little tiny bit of information she gets, okay? She can't read values. She doesn't know what the values are. She doesn't know what the cookie is. She just gets a tiny, tiny piece of information, which is just like, that kind of compressed a bit better than the last thing that you tried. Okay. So say it again. That's right. Yeah. So cookie goes first, then compression, then you encrypt the compressed message. If you compress after, ciphertext looks random and it won't compress. Yeah. So compression is always applied before encryption. Otherwise, it doesn't do anything. Yeah.
So how does this help the attacker?
Great question. Do you have an idea?
By the size of the packet?
So the size of the packet tells me whether it compressed well or not. But my goal is I want to know what that cookie value is. All I'm learning is whether my purple thing compressed well or not. How can I turn that into like learning what that cookie value is?
Doesn't Mallory know the requested value she put?
So I can choose it. Yeah, and she knows it. Yeah, because she chose it.
She can guess the, yeah.
Perfect. Okay, so what if I put guesses here at what the cookie might be? Okay, so I have no idea what the cookie is, so I just start guessing random, and I don't have to tackle the whole cookie. I can tackle a couple bytes. Now, let's say I get one of my guesses is right. One of the bytes in my guess matches the actual cookie value. Is that going to compress well? It will, because you're repeating the same information, right? The same information showing up here, and it's showing up here as well. Okay. Sorry? Yeah, and then I'm in the middle, and again, it's encrypted, but encryption doesn't hide the length of it.
Send the same message upward again and again, so the attacker can actually know the compressed size, and that can be compromised.
Exactly, yeah. So what I'll do is I'll just say I start randomly guessing, like say I put 093a.jpg here. 093a doesn't show up anywhere here. So it will still try and compress it, but it's not going to compress very well because there's nothing repeated.
Attack is made, but not in the level that the attacker be compromised at the end.
I didn't quite get the point. So
It will be so whatever the compression will be happening.
yeah,
It will happen, but not 100% it will be stable.
not 100%. It will be what?
So my question is
Yeah.
that, so the compression before encryption, if we see here, it can be dangerous because the attacker can analyze the compression size and everything in the later steps if we send the same message again and again, right?
Correct. Well, if you send the exact same thing over and over again, then you'll get the same. Like you'll see something of the same size over and over again.
Not
But,
necessarily, for example, in a messaging app like WhatsApp or Instagram, we communicate on a certain topic and we tend to send a similar word, the same word again and again. So that also can be complicated.
yeah, sure. But the attacker here is choosing the message that's being sent. It's not. I'm not attacking what the user happens to be sending. I'm choosing it myself. Yeah. So I fully control this. So I can choose any message that I want. Okay. So what I'm going to do is I'm just going to randomly guess bytes or little chunks of things, like whatever I can exhaustively search. And if I hit, for example, when I get to E33A, because that shows up in the cookie, all of a sudden that's going to compress a bit more than it was compressing before. And then I'll say, oh, I think that that's part of the, I don't necessarily know where it is, but I know that that's kind of a piece of it. And then I'll find other pieces, and then I'll try different orderings of the pieces, and then they'll either compress well or not. And anyway, so you can read the paper, and the paper goes through all the details of how to do it, but it does work in real life.
Can you give a small real-time example of how it works on a daily life, like on a public Wi-Fi or messaging app or something?
So, like, could I do it now, or could you do it in theory? So I can't do it now, but like you can do it in theory. Like they did implement the attack in the paper, and you could read about it and see that it works. Yeah, yeah.
So essentially, the attack is about the compression before the encryption.
Yeah. So it's sort of about all sorts of things, right? But the compression is a bad thing.
Yeah, that's what I'm saying. So
Yeah.
essentially, the exploitation is about the compression because it's about the pattern of the compression.
So I would say it's a combination of like you could take the compression out, the attack wouldn't work, right? You could make encryption not length preserving, now the attack wouldn't work. You could say, oh, we're not going to throw cookie values into headers, the attack wouldn't work. So like there's different ways of removing the attack, but so I have a hard time saying like, oh, compression's the bad guy in the story. All of these things it's just a bad combination of a bunch of things that you should be able to do safely. But because of this weird combination, you're not able to do it safely, if that makes sense. Yeah. Okay, other questions about this attack? Anyways, it's more to show you the sort of give you the intuition, but this is like the level of sophistication of these attacks. So they're not usually like a simple attack like I want to talk TLS 3.0 and you drop it to SSL 2.0. It's not that simple. They're usually like pretty involved. Okay. Yeah, so there's a lot of limitations on this attack. It doesn't work that well. First off, you need to be an adversary that's both in the middle and you have some sort of like scripting control on a browser. You can only steal things out of the header that the browser puts in. Okay. So because you control the request, you can't force the user, like you couldn't steal a password or anything that would normally go in the body of a request. You can only steal things that are in the header. It takes a long time. So you have to look at millions of samples before you can start extracting things. And you're probably going to get shut down by some intrusion detection or something like that before you're able to extract the secret. So it doesn't really work that well in practice, but it does work in theory. And in a lab environment, you can replicate it and run the code and show that it works.
So malware also need to force like the Alice that he needs to send a lot of filters. So how can he force our
Yeah, so in JavaScript, you can do that yourself. So you can run a loop that, and every second you have the power of creating new requests. So once the JavaScript is running, but the user has to keep it open. As soon as they close the browser window, then the JavaScript stops running as well too. So that's another thing I didn't mention, but yeah, like if you're like, wow, my computer's getting hot, or it's like making all sorts of funny noises, like what's going on, like you might just close the website. Yeah, then it doesn't work anymore. Okay, so let's throw this in an attack tree, then we'll go on break. So we can either attack the protocol, the implementation, or the cryptography itself. So we can do some sort of downgrade. We can try and get weak encryption being used. We can try and leak things from the memory of the server, so that's like Heartbleed. We can do side channel analysis, so timing works the best, but there might be other side channels. If we attack the crypto, we didn't go through all of them. We talked about crime, which uses compression, but here's the names of a couple other attacks, that are very similar to crime, but they use, instead of using compression as the vehicle to attack, they use other things. But it's kind of the same idea of pulling cookies out sort of byte by byte by breaking the crypto. Okay, any final questions about this part? Yeah.
So in the previous example, if you have some sort of control over the browser or the user end, will it be more easier to crack the cookie from the browser or the user end? I mean,
if the adversary is sitting on the computer itself.
yeah.
So the cookie, okay, as soon as you compromise the computer, the cookies are all stored in memory on the computer itself. So if you can get access to the cookie jar, as it's called, where all the cookies are stored, then you can just steal the cookies directly. Then you don't need to do any of these attacks.
Like even if I have some control over the browser, getting the cookie is like easy. So
Yeah.
in that case, do I really have to go through all these steps and all this?
Okay, so getting control of a browser is hard because you would have to have an exploit against the browser. Getting tricking a user to come to your website or come to a website that has an ad served by you or something like that, that's a little more reasonable, right? And most users don't think, like, I know we're not supposed to click on links that you don't trust and blah, 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 but our mental model is basically like, if I click on a link, it's not like it's going to blow my computer up, or I shouldn't get infected just from a link. Like, the web should contain kind of the website, and I shouldn't download things and things like that. Then it becomes a little risky, but there shouldn't be any risk really just going to a website. Even if it's purely malicious, if you just go to the website, it shouldn't be able to break out of the website into your browser. Yeah. So this is an attack that works where you don't have to break out of the container of the website. Yeah, everything that Mallory's doing here is not malicious by definition. She's just running JavaScript. She's doing JavaScript commands that JavaScript allows her to do. There's nothing malicious actually about what she's doing here. So that's why it's a powerful attack, is because you don't have to assume that you have exploits against browsers and things like that.
So removing compression was the way to mitigate this.
So it's a sufficient way to mitigate it. Yeah. But you might want compression, right? Like, why not have compression, right? So then you have to think about other ways of
Like
mitigating it.
adding
So it's a good question of, like, what could you do if you really wanted compression? How do you get rid of this attack? The thing is, like, if you pad, then you might as well not compress. Like, you're compressing to save bandwidth anyways, and if you pad it, you lose all that anyways.
what if
So I don't really see an easy way of getting around this attack other than removing compression. It's a good project topic. Okay. All right, let's go for 10 minutes, and then we'll talk about the last sort of segment of the tree. Okay, we'll get started again. Okay, so last class we looked from outside the tunnel. We just gave a light treatment, but we talked a little bit about how you might break into the tunnel. Now we're going to talk about one other idea, which is I can read everything that goes over HTTPS if the tunnel ends at me. Okay, so if I can get myself in the middle, right? Not just in the middle of the tunnel, but actually, at the end of the tunnel, I should say. Then I can read everything, okay? And ideally, I want to do it where the user doesn't know they're talking to me. So the user is trying to talk to Gmail. They think they're talking to Gmail, but somehow they're talking to me instead, then I'm reading all of the emails. Okay, so from the user's perspective, the user can see I have this HTTPS set up, I did this handshake, blah, 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 blah. So from their perspective, they can see there's a tunnel that's there, right? But they don't know where it ends. Where does the tunnel actually end? Okay, so they can see I'm putting messages into some sort of tunnel. Maybe it ends before it even leaves the computer, right? Maybe it ends at the Wi-Fi router. Maybe it ends somewhere in the middle. Maybe it does go out on the internet somewhere, but it doesn't end up at Google, it ends up at the adversary instead, okay? So how do you figure out where a tunnel ends? Okay, so the way that you figure out where a tunnel ends is, again, this will talk about cryptography, but the cryptographic details aren't that important. What people have we have what are called a public key, or you have the option of generating a public key. And when you create a tunnel, what you're actually doing is you're creating a tunnel to a public key. So whoever owns that public key, that's where the tunnel ends, okay? So I have a tunnel to a public key. That's it. It's that simple, okay? All the rest of the encryption stuff you can just forget about, okay? All right, so then it becomes a much simpler question of, I want to go to Google. What's Google's public key? First off, what is a public key? A public key is just a big number, okay? Like whatever. It's like a password, longer and more random, okay? So my simple question is just, I want Google's public key, so how do I get it? And now I'm going to Concordia, I need Concordia's public key. How do I get that key? Where do I get it from, right? Who is it that knows what this public key value is? Okay, if you can solve this problem of somehow you always know what key belongs to what person, then you can always have the tunnel pointed at the right person, and there's no attack here at all, okay? But if you can't solve this problem, then the adversary can always try and get their key substituted in for the real key of the server. Okay, before I show you that, what are your ideas about how you could solve this? Okay, so we could use DNS, so that's one option, so keep that in mind. We could use certificates. Any other ideas? Okay, so what we're going to do is we're going to use certificates first, but DNS is going to come in eventually, not right away. All right, so certificates, what's a certificate? Okay, a certificate is really just a fancy name for there's the identity of someone. So in this case, we'll take their domain name as their identity. So www.concordia.ca, and then there's their public key, okay? So a certificate is just a packaging of the name and the public key, okay? Now, if I let's say I go to Concordia and say, hey, what's my public key? What's your public key? I want to talk encrypted with you. And Concordia sends me back what you see on the screen, but there's an adversary in the middle. What can the adversary do? Okay, they would change the public key to their own public key, right? All right, so this isn't enough yet. We can't solve the problem yet because the adversary can just swap it out. Is there any way I could solve that problem? Okay, so let's play with signatures, okay? So let's say that this is signed. If it's signed, can the adversary change it? Okay, so, or at least they could change it, but you would detect it because the signature wouldn't hold. Okay, so what a certificate is it's a little more than just a binding between these two informations. It also includes a signature, and the signature is from some entity, trusted entity we call a certificate authority, or CA, okay? So global sign in this perspective, okay? So now this comes down the wire, all right? So can I do this attack where I change this key now? Okay, if I change the key, then the signature is going to break. So signatures are specific to the message itself, okay? But I still have two questions for you, okay? The first is, well, what if the adversary changes this signature? So what won't work?
Here, use the fake signature, match the fake public key.
Yeah. So let's say I make a fake public key, and then I also change the signature here. So there's a small detail maybe I'm leaving out, which is when you receive this, how do you check that a signature is valid? What do you need to check that a signature is valid? Yeah, so the certificate is signed, so there's a certificate signature. But what do I need to check whether that signature is valid or not? I need the public key of the person who signed it. Okay? So we have a bit of a problem here, which is the adversary can swap out this public key. So we're going to fix it by signing it, right? But in order to check the signature, I need global sign's public key, right? So I didn't really solve the problem, right? Now it's the same old problem. I need someone's public key. Where do I get global sign's public key from? Okay, so this is the first problem. Okay, so anyways, let me just rephrase it. Okay, so in order to know what Concordia's public key is, I asked for Concordia's public key. They give me a certificate. It's signed by a CA, but now I need the CA's public key in order to verify the signature. Okay, so I just pushed the problem from can I figure out what Concordia's public key is to can I figure out what Global Sign's public key is. Okay, so I didn't really solve the problem, I just pushed it. Okay, so how do I figure out what that is? Okay, we'll answer that in a second. Okay, now a related question is if I can somehow figure out what Global Sign's public key is. Let's say I have some method for doing that, call it method X. Then why do I even need a certificate? Why is a certificate authority signing it anyways? Because I could just use method X to figure out what Concordia's key is. Okay? All right, so that's a sort of related problem. Now there's a second issue, which is that if Global Sign signed this certificate saying this is Concordia's public key, how did Global Sign figure out that that's Concordia's public key? Okay? We'll answer it in a second, but just think about it. How did they figure it out? Again, they have some method. I don't know what it is. Let's call it method X. Well, if Global Sign can use method X to figure out what Concordia's public key is, why can't I just use method X to figure out what Concordia's public key is? Then I don't need this certificate authority or any of this certificate stuff. Okay? So anyway, so hopefully I've convinced you that certificates don't solve any problems at all. All they do is they really just kind of push one problem into two other problems that are more or less look exactly the same as the problem that you're trying to solve. Okay? But the good news is we all use certificates, so we are actually making some useful progress here, even though it kind of looks like we're pushing this around. Okay, so let's tackle these issues one by one. Okay, so the first question before I show you the answer, how do you learn the key of a certificate authority? Does anyone know the answer? Say it louder. Sorry, say it loud. Yeah, so you get the signature out, but I still need the public key.
Yeah, you can always get it two certificates.
So the public key can't be part of the certificate. Otherwise, the adversary could put their own public key and then sign it with their own public key. Well, the private key that corresponds to the public key. So I need to get the public key from somewhere. I have to know what Global Sign's actual public key is to make sure that the signature is right. Because if I have the adversaries instead, then the adversary could sign it. They could say, I'm Global Sign, I just signed this. By the way, here's my public key, but it's the adversary's public key. Okay, so the answer is that you go to the Apple store, you buy a brand new MacBook Air, M4 now, I think, M3, and before you even turn it on, before you connect to the internet or anything, there are a bunch of these certificate authorities keys that are on your computer already. Okay, so they come baked in, they're hard coded in the operating system of the computer. Sometimes when you download a browser, you'll get them that way as well. So like Firefox has their own, we call it a root store, but normally it's with the operating system itself. Okay, so new computers or browsers, they come hard coded with certificate authorities in their public keys. So that's how I know Global Sign's public key. Is CSS, CA certs is like that's the name of a certificate authority, or that's what they're called?
The file that stores.
Oh, I see. Yeah. So it may be on Windows. Is that a Windows thing? Yeah. That sounds right. Yeah. So I only know Apple. Sorry. So I don't know. So in Apple, it's called Keychain. But that's the app that shows it. In fact, I can show it to you. I'll show it to you in a second. But let me show it now. Okay, so these are the CAs that came with my Apple computer. Okay, and so by the way, I'll do something else. So I'm already on Moodle here, so I can go here and say show certificate, and you can see that Global Sign was the CA that matches what was in the slide, and so somewhere in this list there should be a Global Sign CA. So I can go there, and they actually have a bunch. But anyways, one of these ones is the one that signed Concordia's website. Okay, so I know the CA's key because it's hard baked into my computer. Okay, now when you look at this list of CAs, does this look like a big list to you or a small list? Small? How many CAs were you expecting? Yeah, sure. So how many root CAs would you expect? Okay, so this looks big to you, right? Okay, so actually that's, I think what most people expect is there's a couple CAs in the world. Maybe it's just one, maybe there's like 10 of them. Yeah, 10, 11, something like that. But what you can see here is that there's lots. Like, so some of them have multiple certs. And some of these companies, they have different names, but they're actually owned by the same parent company. But if you kind of filter through them, there's about 50 companies here in this list, okay? So a lot of people think that that seems kind of maybe more than you would actually need. So this is just scrolling through. Okay, and the other thing you might notice too is that let me just show you. How many people in the room have heard of ComSign, DigiCert, Global Sign, Intrust, Qualvalidus? Okay. How about Apple, Amazon? Obviously. Okay. So would you say that looking through this list, I know it's pretty small to see, there are some recognizable companies, Apple, Amazon. There's some unrecognizable companies, right, that you've never heard of until today. Is this sort of dominated by the Apples and the Amazons, or is it dominated by the companies that you've never heard of?
Ones that we never heard.
Which one?
It is dominated by the
Yeah.
ones that we never heard.
Exactly, yeah. So most of the companies here, there's 50 of them. That seems like a lot, and I haven't heard of most of them. Like Apple, Amazon, maybe I trust them. I know who they are, but like I have no idea who these people are. Okay. Why does this matter? Who cares? There's 50. What if there were 500 certificate authorities?
Sir, if even one of, like, there is a scammer amongst the 500 ones, then a lot can go wrong.
Okay. So let's assume that one of these is malicious. Okay. What actually can go wrong? How much can go wrong?
We can sign websites that are phishing websites, or like they can take your credentials or something, and they will appear legitimate to users.
Okay, so what they can do is if there's a malicious CA, they can issue a certificate for websites, and they can put their own key, their own malicious key in the certificate, and they can actually impersonate any website on the internet. Okay, So there's no like limitation like, oh, this CA is only for Google or this is only for Amazon, or any CA can sign any website. Okay?
But do we give a priority about these companies? I mean, we trust someone first and the rest is not.
Okay, so you could do that if you wanted, but your computer doesn't do it for you. So your computer trusts everything equally. So it doesn't matter where it comes from. It's either trusted or untrusted. There's no in between.
What if there's a conflict?
What if?
I mean, the same. I want you, for example, I want to access Google.
Yeah.
And the two say give me two answers.
Yeah.
So which one should I trust?
You'll just trust the first one. So as long as one of the answers is sufficient, as soon as you trace back, you're like, I trust that, and then you don't have to hear about it anymore. They can send you more paths, and you can just say, well, I'm already happy. Yeah. Okay, so the reason this matters, this is like probably the most important thing in this lecture, is that any CA can sign a certificate for any website. Okay, so Google might, or Apple might only use themselves. They are a CA. They might only issue certificates using Apple, but there's nothing stopping Global Sign or any of those other CAs from issuing an Apple certificate. And if they do that, and you go to that website, you try to go to apple.com and you get a certificate from one of these CAs, your browser is just as happy as if it came from Apple itself. Okay? So all CAs are sort of equally powerful. So what that means as an adversary is if you can attack just one of them, then it's like you can attack any website. You can get any tunnel of any user pointed at you. Okay, now there's another thing which I'll show you, and then we'll talk about. So if I go back to Moodle, and I show certificate, you can see that like Moodle has a certificate here. So this is Moodle's certificate. You can see its actual public key. I gave you the impression it's just like moodle.concordia.ca and a public key. There's actually a whole bunch of stuff. So you can see there's all kinds of stuff in a certificate. But somewhere in here will be the actual key itself. So this is the key value. So the most important pieces of information are what's called the common name, moodle.concordia.ca, and the key. But then there's a bunch of other information itself. Okay. Now, this certificate is signed by another certificate from Global Sign. This Global Sign certificate is signed by the Global Sign that's hard-baked into my computer, which is called the root certificate. Okay? But there is this like middle certificate. Yeah?
So how do we differentiate between legal websites and illegal ones? Because we don't know if the same, everybody can issue any certificate. So how do we differentiate?
Okay, so we need to answer that question still. So I would say at this point, we don't have an answer to it. But legal is also a slightly different thing. At the end of the day, the best that an SSL certificate will do is it will say, you're really connected to the person that is running moodle.concordia.ca, but it's not going to tell you that they're safe or they're not malicious or anything like that. So anyone can, even adversaries can get certificates, and if they truly run that web server, they can get a certificate for it. So all it attests to is your tunnel is actually ending at this domain, but we're not saying anything about whether it's a good guy that's on the end of that tunnel or not. Yeah, okay. All right, so we have this middle certificate. So you can do certificate chains. So you don't always like have your certificate directly signed by a certificate or a CA that's on your computer. There's often a middle certificate. Why do you think there's a middle here? It seems pointless because Global Sign is the root and Global Sign is the middle certificate. Why don't they just sign it with the root certificate and skip the middle step? What's even the point of having this middle step? So it's more secure in what sense? For me, the user, for the CA?
Sir, I think they generate middle CAs to evenly distribute loads.
Okay, so it could be some efficiency load balancing thing. So that's possible, but it's that may be a component of it, but it actually is a security thing, mostly.
Yeah, if it fails one, the middle one is compromised. You can
Okay.
issue another.
Okay, so if the middle one fails or is compromised or something like that, we can kind of do something about it. So we'll see later there's a process to revoke. If the root certificate fails, you can't do anything about it because it's hard baked into everyone's computer. Okay, so the only thing you can do is do a software update. So the operating system would have to update and remove it from the store. That's a big ask for an operating system to do. So these root certificates are like usually supposed to be like for example, there was an article in Wired about VeriSign, and first off, you only ever need this certificate to sign this intermediate certificate. So what will happen is it's actually usually in physical storage. So think of like a safe, and there's like 10 keys that open the safe, and you have 10 different people in the company. And so they all come with their key, and they go into this safe, and they all open it at the same time. And then they pull out like a little hardware module device that has the key on it. They use it just to sign this intermediate certificate. They put it back in the safe. They lock it all up, and then everyone goes away. Okay? Then 2 years later, they come, and they're like, we need another intermediate certificate. The root certificates are usually valid for 40 years. So let's see when this one expires. So this one expires in 2029. So that's not that far away, but it's still many years. But these intermediate certificates, and also this certificate was first put into computers in 2009. Okay, so this root certificate's 10 years old. It will last another 10 years. But these intermediate certificates are usually only a year. They only last a year or a couple years. Although I guess in this case it lasts 10 years. Okay, so maybe my knowledge on that's a little wrong. But anyway, this is like a 20-year thing, and this is only a 10-year thing. So these intermediates tend to be shorter lived than the root certificates. And there is a process to revoke them that's easier to do than the root certificates. So even if it's the same company that's in the middle, then they'll do this three-chain process just to add extra protection on the root. Yeah.
And I think it also kind of stops the never-ending chain that we saw. That's like the website, and it's signed by an authority, but the authority is signed by another authority, so it has to stop somewhere. So by using the root authorities that are less, I think they're like 1 to 10 or something, so it's less things to manage overall. So it helps it both in security, and also it kind of puts a stop to who's the one leading authority that signs everything else.
Right. Yeah. So the chains have to stop somewhere, and then the important thing is that the amount of power that this, like say you're an adversary and you can either compromise this or you can compromise this, you actually get very similar powers from both. So with this, I can sign any website certificate I want. And if I have the root, I can create another CA that can then turn around and sign any website itself, right? So like they're kind of equivalent as well. Yeah. Yeah.
Can an intermediate CA create another intermediate CA?
Yes. So you can have chains that are longer than 3. So you can have intermediates that create intermediates that create intermediates. There is a limitation in the certificate itself. So the root certificate can put what's called a path constraint, and it can say, I'm only going to allow chains of length 2 or of length 1 or 3 or whatever. And any certificate down chain can put that constraint in at any time. So it's possible to, if you're a root, you can tell the intermediary, I'm going to let you sign site certificates, but I'm not going to let you create other intermediates that create other intermediates that sign. Yeah.
But also, can the intermediary create a root?
So it can't. No. So the root certificates. So the way it works is the site certificate's signed by something, which could be an intermediate. Then you go and you say, okay, who signed the intermediary? There might be a couple intermediaries, but eventually you trace back to a root certificate. It's in your computer, you believe it, and then you stop. Okay. All right. Now the next thing, yeah.
So if a root CA got compromised, could we use OCSP or stuff like that to fix it, or do we have to rely on a system update?
Okay, so save that question for when we talk about revocation, which will be next class. But the answer right now is no, you cannot. So OCSP will work for this guy or this one, but it's not going to work for the root. Yeah. And there's a reason behind it, which you'll see when we talk about the protocol. But basically, someone has to respond to those requests, and it's the issuing CA. But nobody issued anything for the root. And so it doesn't have that chance to do it. Yeah. Okay, now the next thing is these intermediary, we saw in Concordia's example, Global Sign issued an intermediary to Global Sign, and then it signed Concordia. But there's also nothing stopping a root certificate, Global Sign, from allowing some other company to be the intermediary. Okay, so let's say that it wants Concordia to be its own CA, right? It has the power of doing that. It can say, okay, I'm Global Sign. I'm going to issue a CA certificate to Concordia. Now Concordia is a CA, and Concordia can sign certificates for any website that it wants to. Okay, all right. So one question I have is like, how many companies in the world are there that can issue a certificate for any website? Okay, so we think initially that it's 50 because that's how many companies we can see in the root store, right? There's 50 companies here, but because root certificates can issue certificates to intermediaries, right? There could be more CAs that we don't know about. Okay, so here's my question: how do I count up how many intermediary CAs there are?
I don't think there is a limit.
There's no limit to, in theory, how many there are. But if I just want to count how many happen to be operational today, how would I do it? Where do I get that number from? So is it in my computer somewhere? So it's not. Only the root certificates are in my computer. Okay, so I don't have a list of intermediaries in my computer. I just have the roots.
I think the roots can provide the data that.
Let's say they don't. Can I discover it myself? Or some roots are lying, or they're letting other companies do it and they're not telling anyone.
Well, theoretically, to answer the first question, how do we see one from the intermediary? We saw one on a website, right? So theoretically, you would have to go through, I don't know, every website.
Perfect. Okay.
Something like that, and maybe come to, I don't know, but yeah. Probably.
No, that's actually the answer. Okay, so I don't see an intermediary until I go to a website that uses it. That's the only way I see it. I don't know it exists until the first time I go to a website and I see that intermediate certificate. Yeah? And so the only way I can know how many of these there are in the world is like going to every single website. Can I go to every single website?
Probably no.
Probably not. Why?
Because there is no set limit on total possible websites.
Okay, is there a set limit on the total number of possible websites? Why do you think there's no set limit?
Because anyone can host a website any day by buying a domain. So
Okay. So my first idea is I'm going to exhaustively search over every domain. Okay, but I have a problem with that because any string could be a domain. Is there some way I could just go to actual real domains that are registered? Okay, so I could go and figure out which domains are actually registered, and I would see, oh, there's 300 million of them, and so that I could do that. Okay, now let's say that I go to a domain, right? Do I actually end up? How do I get to the website that belongs to Concordia.ca? Do I go to? Does my computer send a package and put Concordia.ca on the outside of the envelope, drop it on the wire, and then it finds its way to Concordia.ca? Okay, I go to DNS. What does DNS give me?
top level DNS.
Well, whatever DNS I do, what does DNS give me? I give it a domain, it gives me something back. IP address. Okay. Is there a limited number of IP addresses? Okay. Could I go to every IP address? Okay. So the answer is slightly complicated than that. There's two versions of IP. Okay, there's IPv4, there's IPv6. I can go to every IPv4. There's not that many. There's a lot of them. It would take a couple days, but I could do it. I can't go to every IPv6. There's way too many of them. Okay, so what people did is they did go to every IPv4 address. They would just write down the certificates they saw. Then they would count up the number of intermediaries, and they found that if there's about 50 companies in the root program, there's maybe another 200 or more that are in this intermediary thing. Okay, and this number is now a lot bigger than when I made the slides, but at the time there was 2 million site certificates, but now it's more like 200 million. Okay, so you can scan IPv4. There's also a project called Certificate Transparency where they try to log every single certificate. It's sort of complicated about which certificates end up in it and which ones don't. So it does have a lot of certificates, but not necessarily everyone. But that's another way where you could see a bunch of intermediaries, and you'll get sort of similar results in terms of the number of companies.
Professor, what about subnets on IPv?
So in terms of certificates themselves, so this is something that I don't think I have a slide on, but I should say. Certificates themselves, okay, actually, let me phrase it as a question. I have a public key, and so I want a certificate. So the certificate's going to be like my name and my public key. Now for my name, I have a choice. I could choose my domain name, or I could choose my IP. Or sub IP or whatever, yeah? Which would be good to do?
Name.
So which name would be better, the IP name or the domain name?
Domain.
Why?
It will be easy to find.
It will be easier.
Otherwise, we need to memorize the IP address.
Well, you don't have to because the browser is going to the IP address anyway, right? So I type in google.com, I go to DNS, I get the IP address. I go to Google by IP address. I don't even send it. I go to that IP address. Google says, here's my certificate. The certificate, and here's my public key. It could say public key and then that IP address that I was just on. Or it could say google.com. Then I actually have to remember what was the DNS thing I asked. So it's actually a little more complicated to use a domain name. Yeah? So the problem with IP addresses is sometimes they get reassigned. Yeah, so if you live in a world of static IP addresses where that's your IP address forever, then sure, bind your certificate to your IP address. But we don't live in that world, okay? So your ISP is going to give you a different IP, but your domain name is yours. That's the assumption, right? Once I own it and I register it, it's mine. It's constant. And so I always bind my certificate to my domain name. But you can bind it to an IP address. Sometimes people do it. Sometimes in a private network where you have static IPs and things like that, then you will bind it to an IP address. But yeah, otherwise you never do. Yeah.
Do these organizations operating the roots CH, do they maintain any database of intermediate keys?
So they should, but they don't make it public. Yeah, so if they issued an intermediary, they should write it down and remember that they did it. But there's no way that you as an end user can go ask them for it and they would tell you. Yeah, there. It's even hard for browsers and stuff to figure it out. Sometimes they're caught off guard. There's some intermediary that they never knew existed. Yeah. Okay, why do we care that there's so many? So now we went from 50 to 250. That seems like way more than we need. First off, why did that even happen? Why are there so many? Right? And so the answer is, well, to be a certificate authority, you basically just start a company and then you convince Google or Microsoft or whatever to put you in the root program. And then now you're a certificate authority. And in the early days of the internet, if you said, hey, that other person's a CA, I should be a CA too, they didn't really have a strong answer to that. They couldn't say, well, no, we're not going to let you, if, there's some difference. And so it became hard for the browsers to have a good reason to say no. Yeah. So it was very easy to become a CA early. Then people started realizing, oh, now we have 200 CAs. We need to do something about it. So now it's a lot harder. If you just start a new CA, you're going to have a hard time convincing Apple or Microsoft or Google that they should add yet another intermediate certificate to the root store. They're just going to be like, we already have too many. We don't need any more. Okay, but this problem of all the CAs blowing up, this is something that happened a long time ago before people really cared about it or really understood that this was a security problem. Yeah.
Now, there are registered issues that you can buy the namespace and ingress. Apart from the original, which are like Apple, Microsoft, and is there like a criteria? Because apparently private, like register, someone can come up and say, if I want to do it, was there like a prior, what's it called, procedure or like a process that needs to be fulfilled before you can become a CA?
Okay, so I want to be a CA. What's the process that I need to undergo? So in the early days, there wasn't a well-defined process, and that allowed too many CAs to get registered as CAs. And at a certain point, we started having problems with the CAs. Then what happened is the people who manage, well, the CAs themselves and the people that choose the root store, so like Microsoft, Apple, like they got together, they created a kind of organization called the CAB Forum, CA Browser Forum. And nothing they do is like legally binding, but they basically sit together and say, this is what we would like to see. And in particular, the browsers can say, if you don't do X, Y, Z, then we're not going to include you anymore. We're going to kick you out. Or if you're a new entrant trying to enter, they can say, this is what we want to see. Yeah, and they write it down. And there are like audit programs that come from the accounting world. In fact, Canada kind of led the way. So CPA Canada had a program called Web Trust. And originally it was like these weird seals that you could put on a website and it kind of meant something. But then people could it was just an image, so you could just paste it onto any website. So it ended up not meaning anything. But like that program sort of pivoted toward auditing CAs. So what they'll do is they'll go into the organization, they'll ask them questions, like they'll meet physically with the people. And then if they're satisfied at the end, then they'll say, okay, you're certified under this like Web Trust program. The problem with it is that the certification is very non-technical. So they'll just go in and ask like a bunch of questions of like, how do you kind of keep your keys secure? And they'll be like, oh, we use a hardware security module. And they'll say, okay, good, check. But meanwhile, they do use it, but like it's sitting in the desk drawer of like someone, like who works there. And anyone could walk up, open the drawer, pull it out, and they have a root CA for the entire web, right? Like, and so the audits were not like substantial enough. So it's kind of an ongoing thing. It's not really resolved.
Because we have like in every country we have different even locally we have CAs that report that an issue in the certificate. They will not talk about the country, then the continent and the region. So it's a lot. That's why
Yeah. So that's a great observation. So where are these CAs? There's 200 of them. So Apple American, right? Microsoft American, Firefox American, Global Sign American, VeriSign American. Are these all American companies? So it sounds that way, but they aren't. Okay, they end up being, especially when you get to the intermediary. That's usually why you issue an intermediary. So some American, some country that doesn't have a CA will say we want a CA. They'll go to a root CA and then they'll say give us a CA. Yeah, and then it chains back, kind of thing. Okay, so the intermediaries end up being countries all over the world. Okay, that's important to keep in mind. We'll talk about that in a second. Okay. Just to move on a bit. So what's the problem with having so many companies? Well, the problem is if any CA can issue a certificate for any website, if I'm a bad guy, an adversary, I just have to compromise one CA. So I just choose the weakest, and now I have 250 companies to choose from instead of 5. Okay? So if I can find one weak CA, then I can break it. Okay? And once I break a CA, then I can get a Google certificate, I can get a Facebook certificate, I can get any certificate I want. Any user that is trying to connect to the real Google, right? If I'm on the wire, I just drop my fake certificate in. I sign it with my breach CA, and then I can terminate their connection at me. then I can reinitiate a new connection to actual Google itself, but I'm in the middle, I'm decrypting everything, I see everything, I'm happy. So this happened a couple times, okay? It started happening, we don't know how many times it happens, because it can happen and no one knows about it. That's what's scary about it, right? So there's no way for you to know that this attack is happening unless if you see it, right? But even if you see it, do you actually know that something's wrong? Because what you are seeing is a legitimate path back to a root certificate, okay? So if a CA gets breached, right, and you go to the website and this breach certificate is issuing a Google certificate, you actually don't know. Maybe that is the CA for Google. You don't know that it's an attack. Like, the attack is indistinguishable from what actually happens, okay? So really the only way to know that it's an attack would be if you were going to your own website and you saw some certificate and you're like, I know that's not my CA, right? Then I would be like, okay, there's something wrong here, okay? The problem is no one was really doing those checks until Google came along. Okay, Google came along and they said, you know what, we're the most popular website on the internet, and now we have a browser, okay? And so there's going to be a lot of occasions where people are going to use a Google browser to go to the Google website. So Google is going to be both the client and they're going to be the server, okay? And so what their idea was, well, we know who our CAs are. We know actually all of our certificates. So why don't we like kind of hard code them into Chrome? And if Chrome ever ends up on Google and there's some certificate that we don't know about, we're going to report that. We're going to phone home to it. So they turned that feature on, and immediately they found there's DigiNotar and Komodo were CAs, and they were issuing Google certificates that Google themselves did not issue. Okay? And then there were investigations, and then the CAs realized that they were breached. The CAs didn't even know it, right? And so people were out there with Google certificates intercepting traffic, and the CAs didn't even know that it was breached. Then it was detected. Then there was a big process of like, do we kick them out of being root certificates? So for DigiNotar, it got kicked out because it was a small Dutch CA. But Komodo, it was too big. There were too many certificates, and if we kick them out, then a whole bunch of websites are going to break. So like we can't kick them out. So DigiNotar got kicked out. Komodo didn't, not for security reasons, just because one happened to be a bigger business than the other. So anyways, that happened. Now that was good for Google because Google is big and they own the website and they own the browser. Okay, but if you're Concordia, you're not going to benefit from that, okay? And what Chrome did too is they said, oh, hey, Microsoft, hey, Facebook, if you want to do the same thing with Chrome, that's cool. Like, tell us your keys and we'll put it into Chrome as well. So if you're a big, like, recognized company, you can get your keys pinned in Chrome. But yeah, it's not going to work for, like, my personal website or Concordia's website or something like that. Okay, then this goes to the other point. CAs are not necessarily like some tech company. We just do crypto, we sign stuff, okay? They're not necessarily neutral. So sometimes CAs are governments, okay? So for example, Department of Homeland Security, they had a certificate. They were a CA for a while. So that's a US government organization. Some of them are not explicitly government, but they're aligned with governments. Okay, so in the UAE, there was a telecom. They got in trouble because they put malicious. As a telecom, they could update people's like cell phones, like the firmware, and they were putting malware, state-sponsored malware. It was alleged into the firmware of phones. Then it turned out that people that's kind of died after a couple of years, like people stopped talking about it. But then someone saw that, oh, they actually have one of these intermediary certificates, right? And then there was a big push to kick them out of it, out of the program. Okay, so in that case, it looked like they were aligned with the UAE government. And then there's some where we don't necessarily know that they're aligned with the government. But the government at any point could legally just go to them and say, give us your private key to your root certificate by law, right? Like we're the government, you're under our laws, and so we're compelling you legally to do that. And they may turn it over. They might try and fight it. Who knows what would happen? Okay. So CAs aren't necessarily neutral companies. So this is some examples of different CAs, different stories that question like whether certain CAs should be part of, should have root certificates or intermediary certificates. Okay, so we answered kind of the first question, but let's just sort of review it. How does Alice know the public key of the certificate authority? The answer is that it's baked into their computer. Okay, now the second part is, why can't Alice use that method to determine the key of the website? The answer is it's basically just a numbers game. So you can have 50 root certificates in your computer. You're not going to have every public key of every website in your computer. Okay, it changes too fast. There could be a new website that just came out today, but your software was updated last week. So there's no possible way that it could know about it. But if your computer knows about a CA and the CA issued the certificate today for the website today, then your computer can know about that or trust that public key. Okay? So that's the reason why you can't use the same method to just figure out what my public key is. You have to go through the CAs. Okay? Now, the second question is, Global Sign signed Concordia's public key. So Global Sign somehow figured out that that was Concordia's actual public key, right? How did it do that? How did it figure it out? I can't figure it out. I need CAs to figure it out for me. So how are the CAs figuring it out? And if they have a method to do it, why can't I just do the same thing? So, but how do they fill the list?
Registration from time to time, then they have connection with the website.
But how do they know? They have the same problem that everyone else has, which is when they connect to the website, they don't know what the key is yet.
They have some contract together, and Concordia have to pay that for this.
So there is a payment that's involved, but how do they still? Let's say I go to the CA and I say, "Hi, I'm Concordia. I'll pay you $200. Give me a certificate for my public key." But I'm actually me. I'm not Concordia.
Domain registration.
Okay, that's a thing. How does it connect though?
So that's how their like uniqueness is predicted, or like the keys are exchanged or stored on the website.
Okay. Let's circle back to that. Kind of right. So I'll go back and then front.
I think they will be asking that, okay, you have to prove us your identity. For that, you will have to show us some documents or show us some email ID that is registered in Concordia's name or something like that.
Okay, so it could be like a process where they're like, okay, send your business documents. Let's call you on the phone. Let's figure this out.
Receipts or registered offices or something.
Okay, so that is a thing. We'll talk about that. Yeah.
Like a federal things, many of them can join a federation and they can exchange their information.
Okay, so there could be some out of band communication between a group of people. That's not the model that HTTPS uses, but it is a model that this whole thing is called PKI, figuring out what key belongs to which person. So like email, like PGP, they had this thing called Web of Trust, which was basically that. Groups of people come together, they exchange their keys with each other, they all sign each other's keys. And so as long as you can find one person in that group, then you can figure out the rest of the people. Yeah. Yeah, so HTTPS doesn't use that, but it is another way of doing it. Yeah.
Using public key or signing by private key, sending to them, something like that.
Yeah, so you have a private and public key, you sign with your private key, you verify with the public key, but this is at the next level, which is just, how do I know that the public key belongs to you?
You have to put it on the website.
Okay, that's fine, but how do I get the public key? Okay, how do I connect to that website and pull the public key down? Can I connect over HTTPS? I can't, because this is circular now, right? Like I need the public key to do HTTPS, right? So before that, but now it's coming down over HTTP. So if an adversary is in the middle, what are they going to do? They can just swap it out, yeah? So that's exactly right. So that rationale, but that's why it breaks down. So I can't just post my public key on my website or it'll break down, yeah. But we'll come back to that idea. We'll play with that idea a bit in a sec. Okay, so let's start with some of the answers. First off, there's two main kinds of certificates, okay? There's what we call an EV or extended validation certificate and a domain validated certificate. So EV certificates are actually probably what you think a certificate is, and it's what certificates were always supposed to be. Okay, they were always supposed to be this, but for reasons I'll get into, they ended up not always being this. But basically, a certificate would be a domain name, concordia.ca, and a key, and some indication of who concordia.ca is. It's Concordia University. It's an organization, nonprofit. It's registered in Canada. It has this address. It has this registration number with the government. Okay? So an extended validation is a domain name, a key, and some identity, whatever identity means. Okay? Now, what we ended up with is we ended up with certificates that just try to bind together a domain name and a key. And I have no idea what concordia.ca is. Is that the university in Edmonton? Is it the University in Montreal? Is it the university in the United States? I don't know. Okay? It's just that's the key that belongs to concordia.ca. Okay? I have no idea who concordia.ca is. I don't know if they're trustworthy. I don't know anything. I just know that that key belongs to that domain. Okay? So this is going to be a little easier to do as a CA, and this is going to be a little harder to do as a CA. It's going to require extra validation, which is why it's called extended validation. Okay, so the original envision of a CA was we're not going to have that many certificates in the world, right? There's not going to be that many e-commerce websites that need them. There's only going to be a couple CAs. And so we're going to do this like business to business kind of thing. They're going to come in, you're going to phone them, you're going to ask for documents, they'll mail them stuff to you, all that kind of stuff, okay? So that still exists. So you can still go through that process. It's pretty expensive to get one of these certificates. And it's not perfect. You could still do impersonation attacks. So for example, there was somebody who worked at Microsoft in IT and they got fired and they were mad. And so what they did is they went to a CA and they said, I work at Microsoft. And they're like, prove it. And they're like, well, here's my employee badge and blah, 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 blah. Because they did work at Microsoft, but they had been fired, but that wasn't showing up, right? And so they were able to get a certificate. Now, it wasn't actually for HTTPS. It was for code signing, but same idea. They were able to impersonate it, okay? So it's a pretty secure method, but it's not foolproof. You could do social engineering attacks. We'll talk about social engineering in a later lecture. So this is just about that particular story. Now, in order to distinguish, let's say I go to Moodle and I'm looking at Moodle, and I know there's like two kinds of certificates in the world. There's a certificate where they check that Concordia University is the University of Montreal, and there's a certificate where it's just bound to moodle.concordia.ca. Which certificate is this? Is this like the good certificate or the bad certificate? The domain certificate or the extended validated? Now you will see that there's like an address and things like that. So it would lead you to believe that maybe this is the extended verification. But even in domain validated, you're free to put addresses in. So they're not actually checked. So you'll get a DV cert and there'll be an address sitting there, but it's just like you could put in the wrong address because the CA's not actually checking that information. Okay, so the answer has sort of changed over time. So what used to happen is if you went to a website that uses one of these EV certificates, they would do two things that were slightly different. The first thing is they would show you something green. Green was sort of the universal indicator. So it might be the bar was green or the lock was green or, whatever. There were different browsers did it slightly different. And the second thing they would do is they would show you the business name itself, not just the domain name itself. So they would usually have a description of, like it would say Twitter Inc. as opposed to twitter.com. Or I guess it's x.com now, whatever. So like that, you would have the business name there as well. So that was the indicator to the user that this was like one of the good certificates. Now, does anyone remember this? Maybe, maybe not. Probably most users, if you're like most users, maybe you saw it, but you probably didn't know what it meant. And if for 4 years you went to Facebook and it was always green, and today you go and it's gray, you probably wouldn't notice, right? You might not even notice if a lock disappears. Hopefully you might notice that. But certainly if it goes from green to gray, you're not going to be like, oh, that's weird. I always thought it was green, right? And so at the end of the day, like users couldn't tell the difference. So the browser just said, forget about it. Like we're not even going to show the user the difference anyway. So now there's no indication that distinguishes between the two, unless if you go digging into the details of the certificate. That's the only way that you can tell now. Okay, then you have domain validated certificates. And so in domain validated, we're just trying to bind the domain itself. So if I'm a CA and you come to me and you're not saying I'm Concordia University anymore, you're just saying I own concordia.ca. I'm going to prove to you that I can control concordia.ca. And if I can convince you that I control it, then you're going to sign the key that I say is my key. And the CA will say, fine. So now what the CA is going to do is they're going to try and test, basically, can you control that domain name? Okay? How could I test whether you can control a domain name?
I think we can show them the documents by the hosting provider.
Okay, so we could go back to documents and things like that. So that's one thing. Another big advantage, I didn't mention it. Let me frame this as a question. Okay, let's say that you have a big e-commerce website and every day you make $1 million. You do $1 million revenue in sales. Certificates, by the way, they don't last forever. So you get a certificate and it has a shelf life of 2 years. Okay, and so anyway, so you wake up one day, you check your voicemails and it's like full and people are panicked and people that work for you and they're calling you saying that we're getting all these reports of users. They're coming to the website and the website, they're getting a certificate error. They're not allowed to go to the website. And the error message is saying the certificate is expired. And you're like, oh yeah, I forgot. Every 2 years I need to renew the certificate. I didn't do it. Oops. Okay. So that's bad enough, right? You lost all of the sales. But now that you've discovered the problem, how do you fix it? You get a new certificate, right? A new valid one. How long does it take you to get a new certificate? Let's say we're in the old world where you're mailing documents and you're doing phone calls and things like that.
2 weeks?
Yeah, it takes a day, 2 days, 2 weeks kind of thing, okay? How much money are you losing every day? Okay, so that was like not acceptable, right? E-commerce sites were like, that is not an acceptable situation. Maybe you could pay a lot to get it expedited. You could say, I'm going to pay you $1 million. I want it done in an hour or two, but you're still losing money, right? And so what people really wanted is they wanted a fully automated, no human in the loop way. So I'm going to show up and my computers and your computers, you're the CA, I'm the domain. We're going to do some conversation or whatever. And at the end of it, I'm going to satisfy you that I control the domain. You're going to issue me a certificate. And the whole thing can be done in 30 seconds or a minute or a millisecond, and I don't have to wait. I'm not waiting a day or a week to get a certificate. Okay? So that was what people wanted. And what the CA said is, fine, we can do it. We can make it fully automated, but there's no way we can figure out your Concordia University, the Montreal University. We can't do that. Our machines can't figure that out. That involves human. But if you want to just prove to us that you control a domain, then maybe we can figure something out, right? We can figure out a way to automate that so that our machines can talk to each other and we don't have to have a human that's reviewing everything. Okay, so that was the birth of the DV certificate. So the DV certificate is the one that's just going to bind these two things together. The reason we like it is you can do it in a fully automated way. How do you actually do it? We'll talk about next class. So you think about it for a week about how you would do it, and then come with your best ideas next class, and we'll see if they're right or not. Okay, we'll see you all next week.